Okay, so I guess we're live right now. Well, yeah, hi, what's up, guys? I'm Jerry, and I'm the head tutor for Signals and Systems here. And yeah, we'll be here to talk about some Fourier analysis, Fourier series, Fourier transforms, and the like. Uh, yeah, if anyone watching right now is on the IEEE Discord, uh, I'm sitting in tutoring room 1 in case anyone wants to come and ask questions live during the stream. Yeah, I have a bit of a presentation. Yeah, oh, hey guys who just joined. Alright, yeah, let's see. Yeah, since this is being recorded, anyone who wants to look at this later can see this already. So I'm going to go ahead and post a link in the YouTube chat. I think I can leave it as a comment. Or I might post it after the stream, but anyway. Yeah, if you look in the chat box, you should see my session slides, and yeah, if you want to follow along, yeah, you can go ahead and download those. So yeah, I'm here to talk about oh yeah, right, I have another announcement. Anyone who is like looking to get some advice about their schedule next semester, the HKN Eta Kappa Nu is hosting an event. Yeah, I think tomorrow night, no, Wednesday night, at 7, where you can ask questions to upperclassmen about your proposed schedule. So yeah, if you have any questions like should I take this professor, like should I take this class, would it be good for me? Yeah, that would be a good place to ask. So yeah, so that's about it with logistics. I'm going to go ahead and start on the content. Right, so let me move back to... Oh, yeah, I can hear you. Oh, right. Let me add that to the Discord too so that y'all can follow along. Wait, one sec. Is there a way I can... Yeah, I'll just add that to tutoring right now. I'm not sure where would be the best place to put those. Yeah, so that's there, if anyone wants to see them. Right. So, cool. Yeah, so, yeah, we're here to talk about some Fourier analysis. So basically, what I'm going to go through is, this is a bit of an outline of what I'm going to go through. We're going to talk about Fourier analysis, of course, and I think that these things aren't all that, they look kind of scary, like with all the math and such, but they're really intuitive ideas, and I think that they're best conveyed with a bit of an application, a bit of an analogy to sound. Yeah, and then we're going to go through, we're just going to talk a bit about the frequency domain in general and what it's supposed to be conveying, just because I think these conceptual ideas are really important to understanding what this course is about. And then we're going to talk about Fourier transform, properties, Fourier series, and I'm going to do a bit of comparison between the two. And then we're going to go into solving some examples after that. So, so yeah, like I was saying, I think that Fourier analysis isn't as scary as, like, once you look at it in the right light, it's not as scary as it might look from the book. It gets really intuitive. I thought it was really intuitive when I thought of it in terms of something that we all know, sound. So what is sound? Sound is like what happens when it's our brain's interpretation of these little sound waves that go from our headphones into your ears right now, and it's it's kind of like this. It's kind of like Fourier analysis in that we have these vibrations, and our brain intuitively knows how to like talk about these things. Like we have we have things that we'll call high pitched, like I whistle. I can't whistle. We'll have like low pitched sounds. It's like someone singing in a low voice. Yeah, we can talk about them being loud, quiet. So like these are all qualitative ways to describe these sound wave signals that reach our ears. So like the only thing that Fourier analysis allows us to do, it allows us to think of these ideas more quantitatively. So like the magnitude and phase spectrums let us talk about how loud a certain frequency is and how it will interact with other similar frequencies. So it's really just this notion of taking this really concrete idea that we talk about colloquially, just turning it into something that we can do a bit of math on. So and like really get exact. So right. So I mentioned the magnitude spectrum. So what is that really? Like you'll go through that in class, but I'm not sure if it's really talked about. Like what does it really mean? Yeah. So the magnitude spectrum tells us like the amplitude of different frequencies. So like we know that a signal like can be decomposed into different frequencies. Like it can be represented as a sum of sines, like the Fourier series. So like we know that. Let me see if I can write here. Yeah, cool. Yeah, so we can represent like some signal like with a sum of sines, and it's just like, and like it can be represented with like the frequency and the coefficient in front, the Fourier series. So that writing didn't seem to work out all that well, but I'll get to that later. I'll go more in detail and give you all the equations in a second. So so some thoughts about the magnitude spectrum. It's like, so it's always going to be just the amplitude, the power of a certain frequency. Like so each of these corresponds to a frequency and how loud it is. Like that, each one of these points is a certain sinusoid at that frequency. So it's always non-negative, and it's going to. Why is it not? Okay. Right, and since we're mostly interested in real signals for the most part. Unless you're in like some area of communications, like that, then like we'll have something called conjugate symmetry. So what this means is that the magnitude spectrum will be the same when you flip it across the y-axis. It's an even function. So yeah, and the magnitude's really important when we design systems. Like we'll typically be talking about our systems in terms of things like our bandwidth. How loud we want things to get at a certain frequency, like the gain, and yeah, like maybe a phase shift that we want, like a time delay, in other words. So like the magnitude spectrum. Oh, shoot. So let's see. Okay, I'm trying to figure out how to go between writing and my cursor. And moving. Technical difficulties. Alright, so yeah, so remember that from the last exam, like if we have linear time invariant systems, then we can completely characterize them through their impulse response, which is basically where you take some impulse function and then you pass it into your system, and then you'll get some function of time that is the impulse response. So, like, this is really cool, because not because we get this time domain function, but it's necessarily because we can transform it into the frequency domain, which tends to be a lot more interpretable. We can tell that at this frequency, this is how it's going to behave. This frequency, this is how it's going to behave. And that's typically how we're going to want to talk about behaviors of our systems. So, like, I mentioned bandwidth a second ago. So just to be clear, like, if we have bandwidth of like a certain signal, then like there's two typical notions of bandwidth. So like, if we have a baseband signal, so what that means is like where if we take the Fourier transform of it, let me see if I can zoom in. Yeah, so if we have like a baseband signal, let's see. I'm going to make this a smaller font. Yeah, so if we have a baseband signal, let's see, so zoom, zoom, zoom. So, okay, a baseband signal is a signal where if you take the Fourier transform, it'll have all of its energy like centered about the x-axis. Like, this is really important. Whereas if you have something that's not a band, yeah, that was so weird. Oh shoot. Yeah, if it's not a baseband signal, then it's going to have like some behavior on the left and right side of the. It's not necessarily going to be centered at the x-axis, so it's going to have like probably some space. I would call this maybe a passband signal. So, like, there's two different notions. So if we have a baseband signal, this bandwidth would be like this half here, the first half. And this is because we'll typically, we can sometimes like omit this left side just because we know it's the same. But for passband signals, it's going to be the full width, so it'll be this whole thing here. That's your bandwidth. And that's because like we might not necessarily have behavior where like we might have things that are asymmetric just because of the domain that you're working in. They might be using complex signals. This is common in communications, and I'm not sure where, like in my personal domain, like audio analysis, like this is what I typically say. Like the bandwidth of our hearing is like 20 kilohertz. Like we can hear up to 20 kilohertz. Like, and that's just the left side of the spectrum. And like we typically will not say that we have 40 hertz by having this left side 40k hertz. Yeah. But anyway, I digress. Yeah, so also a question to the chat. Is there any like issues with the, is everything coming through correctly? Like, can y'all see like my PDF, me writing, stuff like that? Okay, okay, cool. Great. What's that?
I'm happy. You're happy.
Right, right. Yeah, so if you're in the Discord, I think the best solution would just try to listen to me on YouTube. Like, if you can, try muting Discord. I think I'll mute my mic on here. I think that's the best solution. Yeah, so y'all can listen to me on YouTube now. I think that'll like be best, just because I'm not recording Discord along with it right now. So like yeah, let's see. So now that we got the magnitude spectrum, we got the phase spectrum now. So the phase spectrum tells us how frequencies are offset in time relative to each other, and like how they would combine together. Like, would it be additive, or would it be kind of subtractive? What I mean by this is, I'm going to pull up a Chrome tab with a. It's going to have like a sum of sign. Like, I'm going to demonstrate like what I mean by additive and subtractive. So we got. So if we have like a cosine, and if we add the exact same cosine to it, so I add cosine x, then that's great. It doubles in height. Like, notice that this was at 2 before, or that was at 1 before, and now it's at 2. Like, if we add that back in again. So if we like add like some phase shift to this cosine, notice that it's not necessarily going to be it's not necessarily always going to give us some additive. It's not going to just double the amplitude of that frequency. It might be a case where it's completely negates it. So if we have like a is equal to pi, like notice that this completely cancels out everything. So this is a really important behavior to take into account whenever we decompose something into a combination of sines and cosines. So like, yeah, that's what the phase spectrum wants to capture. That is, like, this thing wants to tell us that frequency at frequency 4, then like if we add two of these signals together, then they're going to like add in a way that is according to the phase. So like, let's see, go back to here. So the phase spectrum always has a bounded range, at least when we're talking about it in terms of this course. What this means is that this bounding from -180 to 180 degrees is useful for signals that are periodic, especially, just because like it'll more readily capture this this idea of amplitude, changing. It more captures this idea of like this, that addition doesn't necessarily mean that the amplitude gets doubled or tripled or however many multiples of that same frequency that we have. Right, yeah, so how the frequencies will interact. So the phase spectrum is, it also follows this conjugate symmetry idea. So basically, if we were to take our phase spectrum, you can see like if we reflect across these like y equals x lines, that they're going to look the same. Like if you like rotate the phase spectrum upside down, then you'll get the same thing. You'll get the same function. Yeah, it'll be an odd function because of this. And yeah, sometimes we omit this if like we really don't feel like working with the phase spectrum. For most systems that are time invariant, most of the time, I don't want to say that actually. Yeah, sometimes we omit it because for a lot of applications, the phase spectrum isn't the most important part. It's the magnitude spectrum, but for the context of this course, it's something to pay attention to. So like, yeah, a few other facts. If we have a real and odd signal, then in the frequency domain, it'll be odd and purely imaginary. If it's even, it'll be even. I mean, I'm not saying it'll always be like that if we have a real signal. So it's very likely that you'll only see real signals on your exam, just because most people will want to work with real numbers. There's certain subdomains of engineering that like to use complex numbers to represent their signals, but you'll find more commonly that it's you'll mainly be working with real numbers. Yeah, so this is a important property for us to know. Yeah, so in like I don't think on your exam you're going to find much other than real signals. But yeah, if there is, I stand corrected. I'm sorry then. But yeah, I'm pretty confident about that. Yeah, so yeah, we talked a bit about the frequency domain. So how do we actually get there? We do that through the Fourier transform. It's this integral transform, which it's this integral where we take a function and then we multiply it by this e term, this exponential, and then we get back out some f of omega, yeah, which is a function frequency. And the Fourier transform satisfies a lot of those properties that we went over before, like linear time invariance, the like. And yeah, another nice property that we'd like it to have is for it to be invertible. So this is the inverse here. So if we have the time domain, we can go to the frequency domain with the Fourier transform, and if we're in the frequency domain, we can go back to the time domain with this integral. Yeah, so what this means is, like, usually what this means in practice is that we'll have some real function. It can be like some analytic function that you give as an approximation, like a sine or a cosine or a box. It could be a list of numbers, and you'll see that with discrete data. Yeah, discrete time signals a lot. It'll just be a list of numbers. And when we get this real function, we'll pass it to something that can do this Fourier transform, and then we'll get back out some complex function. Yeah, it's going to be complex numbers that vary with frequency. So remember that it has some real part and an imaginary part. Yeah, a plus jb, if you will. But that form is second to. It's really kind of second to the exponential form of complex number, where we multiply this exponential, which has the phase information and the frequency information, with the magnitude of that frequency. Yeah, and this is useful because, like, it gives us these representations of the magnitude and frequency, or magnitude and phase spectrums that we were talking about. Yeah, like z, like this term in front would be the magnitude spectrum. This one would probably be the phase spectrum. And yeah, it's from this that everything kind of gets defined accordingly. So, like, I think the book spends a lot of time trying to separate the Fourier transform and Fourier series, but like, if you really look at it, they're pretty similar ideas. It's just that how we implement them is a bit different. And really, there's not too much of a difference in the grand scheme of things between the two ideas. Yeah, so, yeah, and I just went over why we use that form. So, one thing that's really important is that the convolution theorem. So basically, if we have the convolution of two time domain signals, then if we take the Fourier transform of that, then we'll just get the multiplication of their two spectrum. Yeah, that's exponential times that exponential form of the complex number. Those two will just be multiplied together, and this is subject to something called duality. So basically, we can any result that we get from the forward transform, the going from time domain to the frequency domain, we'll get some corresponding result for the inverse transform, when we go from the frequency domain to the time domain. And this is really useful because we'll have remember last exam when we were computing all those convolutions, because when we pass signals through some system that we draw as a block diagram, we implicit mean that we're convolving the signal and we're convolving the signal and whatever the impulse response of the system is that we're passing it through. And that gives us X convolution with H. So that's cool. That's cool. So, but convolution sucks. So if we can just do multiplication, we know how to do multiplication pretty well. If we just take the Fourier transform, then we can pass it through, and then we'll just get X times H. And this is a lot easier to implement a lot of times. It's easier for the brain, feels a lot better, and it makes designing systems a lot more intuitive. Right, so right. Mm-hmm. Uh-huh. Yeah, so going from h of t to h of omega. So basically, we just use that convolution, if you really want to derive it for any arbitrary signal, you'd use that integral formula. But what we usually do to make things easy on us is that we use a table of the common integral transforms that we have. There's a lot of them out there. So, and yeah, by using this table, we can kind of deduce if we know that, well, this signal that we're given looks kind of similar to some Fourier transform that we know. We can kind of assume that it's going to have a similar behavior to it under the Fourier transform. Does this make sense? So basically, either it's you're given a really weird function, or something on the table. You might be using the table a bit off. Yeah, I'll go through that in a bit when I start on examples. I hope to get to that in about 30 minutes. Does that make sense? Okay. So, let's see. Going forward. Okay, so, right, so there's a lot of useful properties that come out of this Fourier transform, that specifically come from using this exponential form. Most of them are proved by using this exponential form of the complex numbers, and it makes it easy on us when we're using the table, like good engineers. So like we get these properties where if we shift in time, if we shift a Fourier transform in time, so like if we have if we know that this Fourier transform, this signal is a box, and if we know the Fourier transform of it is a sinc function, then like we should be able to get the Fourier transform of a box that's shifted over in time. Let's say it's over here, and this will be like this sinc function, but just a little changed in the time domain, or not the time domain, the phase domain, the phase spectrum. Yeah, just because like this exponential term it's just a change in the phase. The actual magnitude spectrum would be the same. It would be a sinc function. And yeah, so time shifting is something that turns out to be pretty easy. Time scaling. So if we scale a function in time, so like if we have that same box and we say we scale it, why is it narrow? Yeah, so by scaling, we're just making it either longer or shorter. So like we could have like why is that an arrow? That could be a scaled version in time. This is supposed to be the same height. So this is where the a is greater than 0. It speeds it up. Why is that a circle? I mean, it was supposed to be 0, but what? Technology. Wow. Okay. So that's greater than 0. I'll let it be a circle. And if we want to stretch it, if we went through this in the last exam, but just as a refresher, it's if we want to like stretch it out in time, we would have some a that's greater than 1, or an a that's less than 1. Wait, what am I doing? This a should be this 0 should be a 1. That's much easier to draw. And stretching is a is less than 1, but greater than 0. Right, so what that means is that it kind of has the opposite relationship in the frequency domain. So if we have this scaled box, then we would have a frequency domain representation that would be longer. So if we have like a sinc function, like if this was the normal box, the box of that's scaled, that's shorter, will have a wider Fourier transform. So like it's kind of stretched out and scaled so that the area is the same. Don't forget this 1 over a constant. Yeah. And let's see. We got linearity. So what this basically means is that anytime that we have a block diagram, like the structure is the same no matter what domain you're in. If you're in the time domain and the frequency domain, because like if we have like a block diagram where like we add 2 things, it's still going to be the addition of 2 things in our frequency domain. And that's due to this linearity property. And so that makes designing systems in the frequency domain equivalent to designing them in the time domain. And one other thing I want to touch on here is Parseval's theorem. So what you may know it as is this integral, the energy, is equal to the integral of the spectrum divided by like this 2 pi term. So like you might know it as just this, but it's important because it says that energy is unitary. So like if we had our time domain and it has some area, then like every piece of this area will correspond to some piece of area in the frequency domain. Like the way I like to think about it is like currency, money. So like if we have a certain amount of money in like the US, like we have this many USD dollars. And if we go to Canada and convert them over to Canadian dollars, then like we'll still have the same amount of money. It's just that it looks a little bit different. But should everything go correctly, because I mean that's where this analogy breaks down, but like should everything go correctly, we should have the same amount of money no matter where we go. It's just that it's similar in this signal analysis idea, I guess. Like that's kind of the idea I wanted to put down with this. And it's useful because like if you have like say like the Fourier transform of a function, like, or if you have like the Fourier series coefficients, if you just add those and square them, then you get the energy here, and that's really useful, and it might pop up in your exam. I know that it popped up in one of mine, so yeah, it might be something to think about. So like yeah, I guess I'm gonna go into Fourier series now. Oh, also, are there any questions before we go on? I'm gonna start seeing a bunch of like integrals and like sums. So yeah, I hope that I'm kind of imparting some kind of like intuition here. Like, this is a review for Busso, right? So like, I know in his exams he likes this very conceptual, high-level conceptual type of knowledge in his exams. So like, is there any questions? Like, is there anything that's like not clear? Like, I didn't know what spectrum meant, like, until I left this class, like, so I wonder if someone else has similar ideas. Well, okay. So like, if there's no questions, I'm gonna go ahead and go through Fourier series. Right, so we have a bunch of different forms. Oh, why is there a second E there? That should not be there. So like we got the exponential form of the Fourier series, which is basically just we sum this complex we sum a bunch of complex exponentials together, and because of some math proof, we can reconstruct most of these most signals that we throw that you're going to be given using sines and cosines. And like take note of Euler's formula. That's where we get this notion of sines and cosines. It's made a little more clear in the trig form. So we're basically like we use Euler's formula on this to get these two summations of cosines and sines. So like, and they'll have their own corresponding coefficients that are related to this Cn, this small Cn. And like, also for purely real signals, we have this form, the compact form, which is basically a summation of cosines. And this is interesting because like it accounts for the phase information too. You can see the phase information more directly than in the trig form, but we avoid this scary complex function that really isn't all that bad if we look at it through Euler's formula. So like, yeah, we got a bunch of forms for writing are functioned in as a sum of frequencies, sines and cosines. So yeah, the problem is getting the coefficients a lot of times. So I want to stress that you should try and not do integrals whenever possible. You should try and use your identities to just convert a signal into these complex exponentials. Because I don't know, personally I find them easiest to work with. So yeah, you'll change it into exponential form first, I guess. That's how I'll approach most of my problems. And then if you really need to get it in terms of sines, cosines, you'll use these relations. So I think these are listed on your formula sheet. So it's just the addition of the two trig form. If you have the trig form, you can go to the exponential form. If you have the exponential form, you can go to the trig form. And if you have the... I don't really count the compact form as a real form, honestly. I don't really count trig form either, but we can go back and forth between them pretty easily. The one true one that I have in my mind is the exponential form. So if you really need to, there's some integral formulas for the coefficients, and those are useful if you have a periodic function with discontinuities. So if you have a square or a triangle or sawtooth, which is just a bunch of ramps. Wow, that looks complicated. But yeah, so whenever you're doing these integrals to get the coefficients, two useful identities are this cosine squared t and sine squared t. You might remember them from calculus. So for the exponential form, it's just the integral of the exponential form is just the integral of the function times each harmonic. So this n omega. So there's supposed to be a dt. Yeah, so n omega. Yeah, so for each n, you just keep changing n, and then you get multiples of omega. And then you'll get a bunch of different numbers that you can maybe plot in the frequency domain. Let's say this is a magnitude spectrum, it'll look like a bunch of spikes probably. Yeah, if you're doing this on a periodic function, you'll get a bunch of spikes. So, and if you do the trig form, you'll get something similar. Remember, if you're doing an, the cosines part of the trig form, a0 is going to be this integral, and for all other n, this is going to be the integral that you use. There's a difference of 2, and this one doesn't have a cosine term. And for Bn, it's going to be similar. We don't have to take into account this zero condition, just because Bn doesn't really have B0. If you look at the sum, it starts at 1. Right. Cool, so we got Fourier transforms and Fourier series. So yeah, like I was talking about, they capture kind of the same idea. So just to be specific, the Fourier series is for periodic signals. They need to have a period. And what this will give you is a bunch of spikes in the frequency domain, which is just going to be your C0. Yeah, this is just, if this is your CK, this is just going to be the amplitude and the phase of CK. So you'll have two different plots, and they'll both look like this. Two different plots. And if we go to do Fourier transform, we have Fourier transform to look at signals that aren't quite so periodic. They're going to be continuous in the frequency domain. They're not going to have this list of numbers, the CNs. you'll have to describe the Fourier transform of this some signal as some aperiodic signal as some function of frequency. Yeah, you can't list them out. It'll be, yeah, there's way too many to list out. Right, so yeah, and a few common Fourier transforms that will, I probably should have put this table in, I guess. And this is by no means a complete table, but some of the most important ones, Fourier transform pairs that you'll be using in your problems are, so the complex exponential, that's just a single, that's a single delta function in the time domain, or in the frequency domain. That's a single, whereas if we have a cosine, then that'll be two delta functions in the frequency domain. So it'll be where these spikes are centered at like negative omega naught and omega naught. Negative omega naught. Yeah, so, and I didn't mark omega naught, but the same thing for the first one. So like also we got the Fourier transform of the sine function, which is very similar to that of the cosine function. So in the magnitude spectrum, we'll get two spikes that are at the same exact frequencies, omega naught, omega naught. But in the phase spectrum, we'll get two frequencies that are, we'll also get some non-zero data in the frequency in the phase spectrum. So the sine of this omega naught t, it's like we'll have two spikes where this, notice that there's this 1 over j term, pi over j, but the important one is 1 over j. So 1 over j, remember that 1 over j is equal to negative j. And that one is equal to e to the negative pi over 2j, which is equal to, like if we take it from the clockwise direction, that would be 3 pi over 2, e to 3 pi over 2. So like these are useful identities to know when you're solving problems. 1 over j's comes up pretty often, so this is something to memorize. But yeah, you'll have where at this positive spike, this spike on the positive side, you'll have a 1 over 2. Yeah, you'll have 3 pi over 2 negative, and then you'll have positive 3 pi over 2. Or you'll have positive pi over 2. So this is pi over 2. And then this is negative pi over 2. Yeah, so typically when you're looking at phase spectrums, you're going to have like downward sloping type spectra. So basically this would correspond to like a positive time shift. Yeah, if you were to have something that's like you're going backwards in time, you got like a negative, we'll have like positive sloping things. But yeah, that's a sine one. So like also another important one is the rectangle function. So it's what I keep referring to as a box. So this is a length. This has a length of 1, the unit box. Yeah. So this is centered at 0, and it has energy from negative 1/2 to 1/2 of t. Yeah. So this will give us a sinc function with zeros put at the regular intervals. Yeah, well, with the zeros spaced according to multiples of 2 pi, I believe. No, wait. Yeah, I think these are just inner multiples of omega. Omega naught. 2 omega naught, etc. Yeah, so those are the 4 that I have listed here. There's a bunch of other important ones, but most of them can be derived through this one. Like these 4, they're the ones that are important. Like you'll know that the triangle function is just it's 2 rectangle functions convoluted. Involved with 2 rectangle functions. Yeah, so we got that, and like we'll know that time domain convolution is equivalent to frequency domain convolution. So if you take the spectrum of this triangle function, then you'll get sinc squared in the frequency domain. Yeah, and that's useful for different problems. One other one that's kind of important, as important for sampling, is called the pulse train, or a Dirac comb, or AKA I think it is also called the Shaw function. Yeah, so that's basically where you have a periodic sum of delta functions. So if you have like this guy, where each one of these delta functions is spaced at regular intervals. So then we'll get a Fourier transform that is pretty much the same thing. Like it's just going to be another pulse train. Like so, if we have like writing this algebraically, if like we have a sum from I is equal to 1 to negative infinity to positive infinity of delta t minus n tau, then like we'd get another delta, like sum of delta t, sum of delta omega now, since we're in the frequency domain, minus, I think it's a n omega naught. So like we'll get pulse trains going back and forth between the time and frequency domain. So like this is one thing that's a bit unintuitive to me, because like if we know that the summation of delta functions is like this Fourier transform, then I used to think that it was like going to be a sum of exponentials, but this is a common misconception, and it's something to this is something to remember, that if you get the Fourier transform of a periodic sum of pulses, then it'll also give us a periodic sum of pulses in the frequency domain. So, right. Yeah, so that's really all I have for my slides. Does anyone have any questions before we go ahead and just start solving some problems? So the Fourier transform of a periodic signal would be the Fourier series of it. So like I'm gonna go back to this slide, I guess. So yeah, it's this slide. So notice that for a periodic signal, the Fourier transform of it like we're not really calling it a Fourier transform. Like the book doesn't really call it a Fourier transform. They call it the Fourier series. So all that means is that we'll have like this list of numbers that we can maybe draw out at each of the different frequencies. So like yeah, if we have a periodic signal, then that needs a Fourier series. If we have a aperiodic signal, then we need a Fourier transform. Cool. Cool. Alright, so let's see. I'm going to take one second. What's up? Yeah, it's pretty common confusion. Like one thing that we can actually do, and you might see this later, is that if we have like an aperiodic signal and we just repeat it a bunch of times, that would be a periodic signal. So we would be like inducing like a Fourier series. And basically the Fourier series would be pretty similar to the Fourier transform that we had for that aperiodic version. So, but you'll see that it's just like sampled. It'll be a sampled version of like this continuous Fourier transform. I'm not sure if that's been covered in the class yet, but yeah, it might be covered at sampling. Yeah. Right. So let's see. I'm gonna go ahead and switch over to OneNote so I can start writing. Yeah, because writing on what's it called? Yeah, preview is my PDF viewer is pretty annoying. Let's see, exam 2. Alright. Okay, y'all should see OneNote now. And like, yeah, I'm gonna be tackling a few old questions. So let's see. So like, I mentioned earlier that the sawtooth is a periodic signal that requires like us to do that, like those messy integral formulas to get the Fourier series coefficients. So what I mean is, let's see. So if we have a sawtooth, so like this comes up, and then comes out, down, up, down, up. So like we'll have, oh wait, I drew this off. Yeah, let me redraw this here. Okay, so I'm gonna come down and up, yeah. So it's up, down, up, down, down, up, down. Yeah, cool. So that's our sawtooth. And like this is 1, and this is -1. So like what we need to do is get the Fourier series of this. So what we'll do is use those integral formulas, just because this is like, these are just ramp functions. They're just linear terms. So doing the integral of them isn't going to be too bad. So like, remember the Fourier series coefficients are going to be given by the integral over the period. So the averaged integral of f of x, yeah, so I'm going to call this f of t. So f of t, e to the -2nt. No, wait. -t, e to the and omega naught t dt. Yeah, so if we use this formula, then we should get the Fourier series coefficients of this triangle, this ramp function. So like negative, oh wait, okay, I'm missing a j in this formula, j and omega naught t. Yeah, yeah. Cool, so we just take this integral. So notice that the behavior of this ramp function is going to be just t from the interval from -1 to 1. So notice that our period is going to be, so our period t is equal to 2. So Cn, so just all of them would be 1/2 of our function behavior, so within like our period. So this is t times e to the negative j and omega naught t dt. So like this is an integral that you'll do through integration by parts, but for the purpose of the exam, it will probably just be easier to know the formula for like integrals of the form like t e to the negative t. Yeah, this will be a useful thing to know during the exam, just because you won't have that much time. Time is an issue. Yeah, so like let's go ahead and pull up this integral real quick. Yeah, so I'm a big proponent of using calculators when you've already gone through the class. So I'm gonna go ahead and pull up integral calculator and then show y'all the integral of this t e to the negative t function. So if we go t e to negative t dt, then the antiderivative of this function is just going to be given by this function. So it's going to be negative t plus 1 e to the negative t. So going back to our question, is equal to negative t plus 1 e to the negative t. Yeah, so notice that we have this integral here, so we can kind of apply this formula by just using like a u substitution. So like if we integrate this formula, then we should get something that looks like, yeah, j pi n e to the j n pi t. Does everyone know how to solve this formula, or how to do integration by parts? Is that something I should cover right here? Also, yeah, yeah. Okay, okay. Yeah, yeah. So, great. If I have some time afterwards, I'll go through how to do integration by parts, just for anyone that still needs more help. Right. So I'm gonna go ahead and go through another example. So like, oh yeah, yeah, I can hear you. I can hear you. Yeah, yeah, yeah. So like, we got the integral. So like, there's gonna be a bit of delay between like the Discord and the stream. So I apologize for that. But yeah, this is what we got. So like, another one that might be useful is like just like say without, like if you want like the cosine form, like might want to know the integral of things like t to the cosine t times cosine t dt. So like this will give you something similar. It's you just do integration by parts on this also, and you'd get, let me see, what is this one? T cosine t. Yeah, this is t sine t plus cosine t. Right? T sine t plus cosine t. Yeah, so that's this integral. And you might want to know the one that corresponds to sine. So like so t sine t dt. These are facts that like might speed you up during the exam. So like t sine t, like I think this is going to be negative cosine t plus sine t. Let me check that out. Yeah. So that's correct. That's correct. So we got all these integrals, and these are ones that might be helpful. One that might also come up is maybe like the integral of like t squared sine t, or t squared times all of these. So like t squared e to negative t dt. It's going to be like kind of similar to this one. Like you might have the corresponding t squared for these cosine and sine terms, but these might be something to memorize because depending on what function that you're given during the exam, like right here we have a rectangle function, but that might not be necessarily, or right here we have a linear, a ramp, a sawtooth. So like they might give you something like, say, I don't know, like something that has like quadratic behavior, so between each of these intervals. And this would give you a t squared term. So yeah, these might be useful for when you're given just an arbitrary Fourier series. Yeah, so that's one thing to do. All right, any other questions on this one? Right. So let's see. What's up? Yeah. Oh yeah, definitely. You'll want to be using the you'll be wanting to use those. It's like those kind of escape me right now, but it's like I know that Dr. Busso really hammers those on in his class. So um, let's see. Yeah, it's like my solution just has where we're doing the integrals, just because I couldn't remember these even odd symmetries, but this, it's like, yeah, whatever you can do to simplify your problems, that's going to be the best thing to do. So like if you want to use like even odd symmetries, it'd probably be best. Yeah, so like one thing that you'll probably have to do is get like the Fourier series coefficients for like some arbitrary sum of like sines and cosines. So like if I have like f of t is equal to 1 plus cosine, I say like 2t plus sine 4t plus 2e to the j 6t. Right, so how would we get the Fourier series coefficients on this? It's like if you remember those formulas that I gave for cosine and sine in terms of the exponential function, like remember that cosine t is equal to e to the jt plus e to the negative jt over 2. And same thing for sine. Sine has a similar formula. Cosine of t, or sine of t is equal to e to the jt minus e to the negative jt over 2j. Right, so we got these two formulas. So for this problem, what we'll want to do is get the Fourier series. What I'm going to do is get the exponential form of the Fourier. We're going to get the exponential form, and then we'll have those coefficients. And if the question asks for like the trig form, we could go through that, or the exponential form, or the compact form. So like I think that you have those relationships on your formula sheet also. So let's see, I'll go ahead and do this one real fast. So this one is like, so f of t is equal to, so this one term is, yeah, so this is j0 t, yeah, e to 0 pi, yeah, is 1. So cosine is 1/2 e to the jt, j2t, 2t, plus 1/2 e to the negative j2t, plus 1 over 2j, e to the j4t, plus 1/2, minus 1/2 j, e to the negative j4t, plus this last term's already in the exponential form. That's great. So like 6t. So we got, this is c0. Notice it's a 1. This is c2. This is c2. So this is c negative 2. This is c4. This is c negative 1/2. So like, notice that so when you're doing these types of problems, you'll want to get the fundamental frequency of all of these sines and cosines. So you'll notice that yeah, omega naught is equal to the, I think it's the least common multiple of all of these terms, or lowest common denominator, yeah, of these multiples of this 2. So like 2, 4, 6. I think the lowest common denominator of all those is 2. So we have omega naught is 2. So we got, this one is actually going to be not c2, but this is going to be c1. This is c negative 1. This corresponds to c, yeah, so this is c2. This one's negative 2. This one's 3. So like, yeah, in the end we'll get something that looks like this. C0 is 1. C1 is equal to 1/2. And negative 1 is the same. C2 plus minus 2 is equal to, yeah, so C2 is equal to 1 over 2j. C2, negative 2 is the minus of that, and then C3 is 2. So this is a problem that can be done pretty quickly. If you were to really just apply these formulas, most cases it's like you'll see these omega terms, like these frequency terms, the 2, the 4, the 6, and a lot of times you can just kind of look at it by inspection if you get enough practice. Like, so this one would be like C1, C2, C1, BC2, C3, or plus minus 2, plus minus 3 if there was a cosine term and sine term. Yeah. So yeah, that's how you turn a function that is the sum of cosines and sines into this Fourier series. Right. So I'm gonna go ahead and try and craft an example here. So like, if we have like a, yeah, I assume that there's no questions on this one. So like, if we have some signal x of t, and let's say that that one is just going to be a rectangle function. I love rectangle functions. And this is going to be from 1/2 to 1/2. Then how do we get the inverse Fourier transform of, yeah, this, how do we get the Fourier transform of this x of t whenever we have it shifted over? Yeah, so we have x of t minus, let's say, 4, and we also scale it in time by 2. Yeah, what would the Fourier transform look like? This is, so like, if we use those properties that we were talking about, so like, if we have like, I'm going to write those in red. So xt minus tau, and then corresponds to some multiplication. Yeah, so x of t minus tau, that's negative j omega naught tau, j omega tau times x of omega. And similarly, like if we have the scaling, so x times a t, that corresponds to e to this 1 over a times x of omega over a. Yeah, so those are two identities that we use here. So if we want the Fourier transform of this one, then we'll get, yeah, 1/2, so x 1/2 t over, so this is equivalent to minus t over 2 minus 2. So like, if we apply the frequency shifting, the time shifts property, so this will give us e to the negative j omega 2 times x to the times the Fourier transform of x of t over 2 x. Right, so we got that. And what's the Fourier transform of x of t over 2? So we got that we got to use this scaling property. So it will be 2 e to the j omega 2 omega times x to the 2 omega. Yeah, so this is going to be your Fourier transform for this rectangle function. So like, we remember that the rectangle function is, it gives us a sinc function in the time domain, in the frequency domain. So like, it's going to be a sinc function. So I'm just going to plug sinc in here. So we got e to the negative j 2 omega sinc of 2 omega. And that's our Fourier transform. Yeah, so that's x omega. And yeah, you got that. Right. So any questions on this one? Right. Also, one thing that I forgot to mention during the slideshow is something called Gibbs phenomena. So that's basically where, like, if you're trying to take the Fourier series, like if we're trying to like represent a signal with the Fourier series, one that has like discontinuities, then it's going to converge to something similar, but it's not going to be quite the same function. It's very similar, but here I have a bit of a demonstration, I guess. So like, if we want to get the, so let me see, let me switch over to Chrome. Yeah, so if we want to get the Fourier series of a like a not a sawtooth function, a square wave, like a bunch of pulses, like that. So then, like, well, this would be the Fourier series that you get. It's just a bunch of sine waves. So like, we got 0 harmonics added right now. Remember that the Fourier series goes from 1 to infinity. We're using the trig form. So like, and I'm adding 0 harmonics right now. So like, it's completely flat. All we have is the DC term, which is 1. But notice that as we add harmonics, it'll slowly start getting more and more square. So like, great. So like, it's starting to look more square, but like, it's not exactly square yet. So like, what if we turned up the number of harmonics that we add? So we keep going. So we already have a lot of harmonics right here, but it doesn't look like these end behaviors are going to go away. These sudden spikes, and that's because of discontinuities. So anytime that you have a signal that isn't necessarily going to have like that you can't really write with like just one function, it's got like a piecewise behavior. So I've called it in the past. It's like, then you're going to have some kind of like spiking that occurs at these discontinuities, and that's what we call the Gibbs phenomena. So like, yeah, if we keep adding harmonics, this will never go away. But like, these harmonics will, it's like as we keep adding harmonics, this will get more and more flat. So like, that's what you need to know for Gibbs phenomena. There might be a question on that. Right. So let's see. Let's go back to examples. Okay, so let's say I wanted to pass a signal into a system that we have. We already know the impulse response and the Fourier transform, and we want to get something from that. We want to get the output. So we'll be making use of the convolution theorem here. So like, I've got to take a minute break. I'll be right back. But yeah, think about this while I'm gone. Alright, so I'm back. And right, so we're going to be passing a signal into a system. Where'd my pen go? Right, so if we have a okay, there we go, there's my pen. Yeah, so if we have like some signal that we know the magnitude and the phase spectrum, so we have x omega. And let's say it's like a triangle function. And we have the frequency domain, the phase spectrum of this. And like let's say we know that it's linear phase, so like it's just a straight line across the time domain. Not the time domain, the phase domain. So this is phase x omega. It's a straight line. So like this is going to be pi over 2, and this one's negative pi over 2. And this one, and like it has a bandwidth of omega naught, negative omega naught, omega naught. And this one also has corresponding bandwidth of omega naught, omega naught. Right, so if we have this signal right here, and we have this system, so we have the magnitude spectrum given by h omega is just a box. It's going to be a rectangle function where these two are the same, so which has like a slightly smaller bandwidth. So yeah, this is omega 1. This one's omega 1 negative. So this one also has like, this one has a piecewise phase function, so which has a bandwidth of omega 1, and then this is pi over 2, no, this is pi over 4, this one's pi over 4. Right, so this is h omega. Yeah, so what we want to do is get the output, the y function. So is pretty simple solution. I'll remember the convolution theorem, where if we pass x into h, then y is equal to x convolved with h. And if we take this into the frequency domain, then if we have, so we'll have x omega. If we pass it into the impulse response, h omega, then we'll get the frequency response of y, which is x omega times, not convolved, times h omega. Yeah, so we got that. So what this becomes is just we're multiplying the magnitude spectrums and we're adding the phase spectrums. So what this gives us is something that looks like this. I'm just going to denote that omega 1 is less than omega 0, just for clarity. Right, so we got this omega. Okay, so we need to multiply the magnitude and phase spectrums. This comes from like the idea that like y, like the magnitude of y is equal to the magnitude of x and the magnitude of h added, or multiplied, and the phase spectrums would be added. So y is equal to phase spectrum of x plus the phase spectrum of h. And these both come from like that exponential form of the exponential form of our signal. So all we have to do is add the values here. So we got right? So x had a bigger bandwidth, so I'm going to start off with this triangle function, and then I need to multiply it times this rectangle function. So this rectangle has a 1. Yeah, I'm just going to say it has a 1. So like outside of omega 1, then notice that everything's 0. And remember that anything times 0 is 0. So if we multiply these two together, then we'll get like just the behavior that exists within omega 1. So this is omega 1, omega 1. So notice that it's just this triangle function, but it's just cut off a little bit. And we'll do something similar for the phase spectrums, but instead of multiplying, we're adding. So if this one is a ramp, so if this one is our original X phase spectrum, then we got to add this pi over 2 and pi over 2. So like if we add, wait, this is pi over 4, so a negative pi over 4. So like this would give us something that looks kind of like a linear function, but this one would be like up. So that's pi over 2. It's pi over 4, I think. So like, and then this one would be down. So like that. Then we'd go back to the regular behavior. Oh, right. Okay, so I'm going to draw that a bit better. Okay, so I think that'll intersect there. This one will be like there. And then this diagonal would be up. So like, notice that outside of this omega 1, this is exactly the same as our linear function. Yeah, so yeah, those are our magnitude and phase spectrums for y. And this is phase. Any questions on this one? Pretty much. It's like the way that I would recommend to do these types of problems, especially if you're given the pictures already. I think that's kind of a hint that he wants you to use the graph somehow. But yeah, if you already have the pictures, then think of it more graphically. Just multiply like by just lining them up and seeing what you get. For the most part, when you're given like things with graphs, you'll have behaviors that have like zeros outside of some band. So like, so outside of omega 0, everything is 0. Everything inside of omega 0, that might actually have something in there. So like, we only have to pay attention to those. But like, yeah, we'll also have like 0 terms like outside of omega 1 here. So like, this region between here is subject to get cut off. That's something that we call a filter, by the way. Mm-hmm. Yeah, since this value is 1, it's like anything that's inside of here will just be the exact same. Like, I didn't mark a value for y here at this tip, but I mean, we could have it be a, and this would still be the exact same question. Yeah. Oh, what's up? I thought this was 3302. Yeah. Yeah, it's like, so yeah, this is kind of an important idea. It's like, because it kind of encompasses yeah, the idea of filters that I'm sure you might have heard by now. And yeah, this is for the case when we already have the Fourier transforms. So like, let's go to a question where like we're working in the time domain. Like if we want to have, if we have like x omega, and if we have like x of t, and we want to get omega. If you have x of t and h of t, then what do we do if we want to get y? So like, you'd carry out a very similar process to this actually. You would, so let's say that we have x of omega, or x of t. So this is a time domain now. So if we have, let's see, what do I want to do? I want to have, like, say, like a sinc squared. So a sinc squared t. So this is a very, very good question. So what does this look like? Let me go ahead and try and graph this real quick. But you know, screw the graph. We don't even need that for this question. So if we have x of t is sinc, it's just and then if we have h of t is equal to sinc of t, yeah, the sinc function. So what we'll get, so what we'll want to do is we'll want to get y of t is equal to x of t convolved with h of t. So remember the convolution theorem, so yt, so y omega is equal to x omega h omega. Same thing as before. So what we need to do is get x and h omega. So recall that the Fourier transform of sinc is going to be a triangle function, so x of t. Yeah, there's a certain reason why I chose sinc, because yeah, if we get the Fourier transform x of t, then we'll get the same triangle that we had before, like omega naught, like for some omega. Yeah, so adjusting for constants, it's like we'll have some triangle, and then if we have an h, so if we take the Fourier transform of h, then this will give us, remember that the Fourier transform of a sinc function is a rectangle. So this looks pretty similar to something that we saw before, like this question. So we would really just kind of carry out the same process where we take the Fourier transform of these two time domain signals and then do the convolution with the Fourier transform. We don't want to do convolution. We avoid that by doing this. So what we'll want to do to get y of t now, because that's our goal, is we'll take the inverse Fourier transform of whatever our function here was. So I'm going to go ahead and copy these over to the other slide, because that's kind of where I was getting with this. Yeah, so let's see. So we already have the Fourier transform of y. So we just need to get the inverse. So like, let's see. Let's move this up here. This is y. Cool. So let's see. We got a triangle function that is cut off. So let's see. I had this. Like, I'm going to say that this one was t. Yeah, t over 2. And this one was. That one's negative t over 2. This side is positive t over 2. Right, so, and this exists from -1, or negative omega naught, negative omega 1 to 0, and this one exists from the opposite. So it's a plus t. Yeah, it's like, I'm just kind of parameterizing these lines from the graph right now. So yeah, what we'll want to do is take the inverse Fourier transform. So like, this doesn't look like anything that'll probably be on your table, so what you'll have to do is do that that inverse transform. So f, been doing it with curly f, curly f curly. Alright, so we got f inverse of yt, y, and then inverse. So what we'll have is, we'll have to do the integral from, so we'll have two cases. So like, I'll do this one case right here. So omega naught, 1 over 2 pi over negative infinity of t over, so y omega times e to the j omega t dt, and this is going to give us two integrals because like there's two different behaviors, so we'll need to add those. So this is going to have, wait, why did I draw this brace? Yeah, so 1 over 2 pi times integral of yt, which is t over 2 plus a e to the j omega t dt from 0 to omega naught, okay, omega 1, oh wait, this was the other bound, 0 to negative omega 1 plus the integral from 0 to omega 1 t over 2 plus a minus e to the j omega t dt. So yeah, after this, you'd basically just do a bunch of integration, and then from there, you'll get your answer. This will give you both. This will give you a real function in time, probably. Yeah, I'm pretty sure this gives you a real function in time. So like, you carry out this integral. So like, remember those integrals that I went over in like one of the first few slides, where these are will come in handy here, because like you can just do a bunch of algebra and reduce it to these forms, and then copy paste. So like, yeah, that's your inverse transform for y. Does anyone have any questions on this? Okay. Yeah, so like, if we have this x of t, and we got the h of t, so what we want to get is the output signal y, which is what we get from passing x, the time domain signal x, into our system with impulse response h. So remember the convolution theorem, so multiply x and h in the frequency domain. So how do we do that? We got to get the frequency domain representation of x and h. But since we did that in the last problem, I got our frequency domain version of y by just taking our solution from last problem. And like, in general, you won't have that already. You'll have to find it, but yeah, I tried to make it easy. But yeah, basically from there, once you have y, you'll just take the inverse transform. That's kind of the idea of this question. It's kind of supposed to be a demonstration of filtering. Oh yeah, definitely, definitely. Yeah, so like it's a similar process. It's just a matter of taking the convolution. Or are you unclear on how we got where, like the Fourier transform of x or h? Because like these two I'm kind of taking from the table. Yeah, yeah, exactly, exactly. It's whenever possible you'll want to use the integrals from your table. Like those are going to be the easiest to carry out most of the time. So like let's see. What's another example and something I haven't covered yet? So like you're probably going to see a block diagram or two. Let's see. Trying to think of something. Oh, also I should cover something that uses Parseval's theorem. Yeah, yeah. Cool, cool. Right, so let's see. Let's say we had like some signal that we're passing through. Let's say we had a system, actually. Let's say we had this system, like H. It's in the time domain. So like, what we'll want to do is get some signal input X, and then we pass it into something that scales it, X to T. Yeah, yeah. We want it to scale it in time. And then what we want to do is we want to add it to itself. So I'm just going to add them here. So like, let's see. What do we do here? And then we'll get y. So let's see. If we have... Okay, wait. I think this is a bit too simple. It's like, why are we adding it to itself? We could just multiply it times 2. So like, what if we want to process those two signals differently? So like, what we'll want to do is, let's get x of t. X of t plus 3. And then we'll want to shift this one a different amount, x of t plus, say, 1. So, and then add them back together. So my question is, how do we get the impulse response of this system if it's defined like this? If we only know it's in terms of x. So like, what you want to do is pass in the delta function. So like, this might be something that you might not necessarily be given the impulse response, or the you might not necessarily be given like the impulse response, or like what you're given, or the frequency response of our system, but instead how it operates on the input signal. Like, you might be given something like that. So what you want to do is pass in the delta function. So if we take, say, delta, and then we go, and then it runs through the system, what do we get out? So let's see. I'm going to write y in terms of all of these x of t's. So y of t is equal to x of t plus 3 plus x of t plus 1. But all of these intermediate signals are actually, so I'm going to call this x1 here. So like this is actually an intermediate signal to our original x. So we're going to compose these two. So we're going to get, so x of t plus 3. So it's like we'll need to timescale x of t. So let's see, what would this be? T plus 3. So x scaling comes before. So I think this would be 2t plus 3 plus x 2t plus 1. So what happens if we replace all of these things with delta functions? So like y of t is equal to, so like if like our impulse response is just going to be the output whenever we put in a delta function. So I'm just going to write h of t is equal to delta 2t plus 3 plus delta 2t plus 1. And that's it. That should be our delta functions. So that'll give us like wherever this is 0, so this equals 0 at negative 3 over 2. So this gives us a spike at negative 3 over 2. And then this one is 0 at 1/2. Yeah, negative 1/2. Yeah. So that's our impulse response. So like, what would we do to get the? It's kind of a trick question, but like since we have this h function, and what if we had a given x? Like this is our impulse response now. So what if we want to get the output when we pass in, say, like a rectangle function? Love me rectangles. Right, so we got that. So this is a bit of a trick question. So as I've said before, the easiest way to do most of these questions is to do x time. Yeah, in order to get x of t convoluted with h of t, then what you'll want to do in most cases is x omega times h omega. But remember that when you have a delta function, when you convolve with a delta function, it's just going to place a copy of our signal at that point in time. So like what that means is like we'll just get copies of our x of t at negative 3 over 2 and negative 1/2. So like the easiest way to get the output signal whenever you have an impulse response that is a sum of like delta functions a lot of times is just to like place these copies of our input function at those 2 points. So this would be like box 1, box 2, this one's centered at, let's say that's 1/2. And that's 3 over 2. Yeah, it's like they'll just get a bunch of copies at a different point. Is there any questions on the idea here? It's like we want to get the easiest way of getting the output given the input. Right, so since there's no other questions, I think that's really all there is to this exam, really. We did a few questions on Fourier series. Yeah, it's like you'll need to get the coefficient somehow. So you might be given a Fourier series that you'll have to get into different forms, or you'll either have to compute the Fourier series using some notion of like either the properties like we were talking about, or just straight through the integration formula. Um, yeah, it's the easy way of doing Fourier series when it's like just sums of sines and cosines, or exponential or complex exponentials, is like just using uh, the formulas for cosine and sine. Yeah, whenever we get it'll be important to know the properties. So a lot of these questions could be simplified probably further by using some of these, like the time scaling, the frequency scaling, time shift, frequency shift. Yeah, all according to those equations. Notice that it's just a matter of multiplying the frequency response or the time domain signal by some constant, like that exponential term or that 1 over a term. So like we got that, and yeah, we got some notion of filtering. And it's just like where when we have like some band limited filter and we multiply it with our signal, then it cuts off things outside of that filter's bandwidth. And this is I almost assure that you'll have some similar setup to a filter on the exam. Uh, yeah, other than that, is there anything y'all wanted me to cover in the last like few minutes we have here? Oh yeah, yeah. I'd appreciate seeing the picture. Yeah. Okay. Oh yeah. Yeah. So what the question is asking is, so we have a function that is defined in terms of its Fourier series. So this was on one of the homeworks. So let's see. So x of t is equal to sum from 0 to infinity, k is equal to 1, 6 over k sine squared k pi over 2 times cosine of 1600 k pi t. Oh boy, Dr. Busso. So just a bit of a tidbit, 1600K is like a very common number when you're working with audio. So I think that's where this might have come from. Yeah, so we got that. So we got, so I'll full screen this here. So we got this function that is defined in terms of its Fourier series. So we have a low-pass filter also that blocks anything above 200 hertz. So let's see. What that means is that we have a filter that above 200 hertz, then it cuts it off, like everything outside of that. So that's our H. That's our H omega. So what you want to do is get the Fourier series coefficients. What you'll want to do is get the Fourier domain representation of our x of t. But this is easy when you already know the coefficients a lot of times. Because like, if you look here, our cosine, this is like a compact form, right? So this is just multiples of the 1600k pi. Yeah, so that's compact form. So remember that this is of the form like, so I'm going to put that formula in red. Yeah, so it's k from 1 to infinity of an cosine and, oh wait, ak. Okay, we're using k. Cosine omega naught k t plus like some, plus like a phase term if like you have that. So like, oh, what is that? So plus omega, I'm gonna say theta k. So like, that's that. But since we have the coefficients already, all we need to know a lot of times is just the magnitude spectrum, especially when, and like, because like we can often ignore the phase spectrum whenever it's just completely zero. Like 0 plus 0, it's always going to be 0. So like, the Fourier coefficients of this compact form are purely real, so we're only going to get real values in our frequency domain. So like, so x of t is equal to, wait, x of omega, because we want the frequency domain version of x, is just going to be like the different values of this. Since these are our coefficients, we can just plot these as like delta functions. I think this will like decay like something like this. Yeah, so like, and this would go on for like forever. I think this is like, these would be at the multiples of 1600k. So I think this is like 1600k. Hey, this would be 3200k. This would be 48, 64. So like, if we were to just take the output now, like since we know our Fourier transform of x, and since we know the Fourier transform of h, our filter, then we can just cut off everything that's in here. So like, notice that this has a pretty low bandwidth, so like 200 hertz, whereas all of our stuff is above 1600k. Like, so that's why this question works out to being like 0. Just because like, I don't think that there's a DC term here. Like the DC term, like if we had like an A0, that would correspond to the center, but since we don't have an A0 here, then there's nothing in the middle. So since all of the higher order harmonics are outside of our filter's bandwidth, then we got 0 in our output, so that's y omega. Is that a little more clear? So like, if we had something in between negative 200 and 200, then we actually have something in our output. Like, but since we don't, then this filtering this signal with this system gives us 0. Like the answer would change if like we had like some omega that was like less than 200. Yeah. So that I guess that's it for the review session. I can't remember if there's anything I missed. Yeah. So like also yeah. So like I guess that's it. Good luck on your exam, y'all. Thanks for participating. Yeah. Y'all have a nice week.